Hi, everyone. This is Prof. K speaking, and today we're going to be talking about the properties of liquids. So our learning objectives for today are to distinguish between adhesive and cohesive forces, to be able to define and use viscosity, surface tension, and capillary rise, and then start to talk a little bit about the roles of intermolecular attractive forces in each of these properties and phenomena. And so to start off, I want to define viscosity. So viscosity is the measure of a liquid's resistance to flow, and we quantitatively measure this using a viscometer, which determines the rate at which a metal ball falls through a liquid. So I have the same tube here in my viscometer, I have the same metal ball, and I measure the velocity of that ball as it flows downwards in the tube. And the differences in velocity tells us about the differences in viscosity. So if something has a high velocity of the ball as it rolls back and forth, that means that this liquid is potentially pretty thin and pretty fluid so that this ball doesn't experience much resistance to its flow. And what that means is that its viscosity of this of the one that's larger, has a larger velocity, is going to have a smaller viscosity. So if our velocity is small, then this ball is significantly hindered by flow as it moves down this tube. And that means that the viscosity of the liquid is high because it's really able to resist the flow. And so if you think about real world examples of low viscous liquids, you might think of something like water. It flows really easily around substances. On the other hand, a material with a high viscosity might be syrup or glue as it's drying. And so these are liquids that don't like to flow, and they have high resistances to flow. So if something has a high viscosity, it doesn't like to flow. It's resisting flow. And so this is just one property of liquids that we'll see and we'll talk about. And you can think about if something has really high intermolecular forces, so there's a lot of interactions between molecules in this liquid here. If these intermolecular forces are high, then it's harder to flow and it has a high viscosity. Whereas if something has potentially smaller intermolecular forces and it's easier to move, it might have a lower viscosity. Another type of force that we like to talk about with liquids is a cohesive force, intermolecular forces between identical molecules of a substance. And so we just talked about this in our last video. We're having dipole bond interactions and dispersion interactions. And all of these will work together to hold or keep cohesive that material together. And so the water interacting with the water inside a droplet is going to be called a cohesive force. It's what's holding our liquid together. And if you're in the center of our drop of water, this water is going to feel cohesive forces equally around it as it's interacting with these other molecules. On the other hand, on the surface of our liquid, it's going to have some asymmetric interactions with the interior surface or the waters, the cohesive forces that are pulling it in, and potentially this open surface where it's not experiencing forces from other molecules. And so you often end up getting these spherical shapes that are caused by this asymmetry, and waters attempt to try to limit how much surface area is exposed to something else when it would prefer to just be interacting with other waters. And so this concept of having this surface that water's trying to hold together, or that other substances are trying to hold together, has been identified as a surface tension. And surface tension is the energy that's required to increase the surface area of a liquid, or in other words, the force required to increase the length of a liquid surface. And that's not necessarily intuitive to me, but how I think it can help me think about this is the surface tension is how hard it is or how much energy I have to put in if I want to break the surface of the liquid. So these water striders rely on the fact that water has a high surface tension to keep them from falling into the water. If it were easier or took less energy to break the surface of water, the water strider couldn't stand on the surface of our material. And so the fact that water is holding itself together and has this surface tension allows us to resist other things breaking into this. But you can imagine that if you add something to the water, you can break the surface tension or break how well the water can hold together. So if you've ever watched Olympic diving, sometimes what they'll do is they'll bubble water, or they'll bubble oxygen into the water, or they'll put soap into the water to break the surface tension of this, so that the divers have to spend less energy breaking through the water as they do their dives. So it makes it safer because there's less transfer of energy when they hit the water. And so surface tension helps us describe how we break up these intermolecular forces that the water is experiencing and move through the surface of some material. And we also have, with liquids, adhesive forces. And what adhesive forces are the attractive intermolecular forces between two different molecules. And so in this picture, the droplets of water are water interacting with each other, and that's cohesive forces, but they're also clinging to this web. And the way that they cling to that web is through adhesive forces. So it's some material interacting with a different material such that they're still attracted, even if it might be in different ways. And because you might have different amounts of adhesive or cohesive forces, it's possible that different liquids will behave differently when they interact with a material. So for example, one of the sort of experiments that we'd like to look at in this case is the relative difference in adhesive and cohesive forces for mercury versus water. And so in our left beaker here, we have mercury in the beaker, and the cohesive forces of mercury are higher or stronger than the adhesive forces between mercury and glass. So the mercury tries to pull up and pull away from the glass. So you can see it sort of raising up above the glass because it's pulling itself and trying to touch the glass as little as possible, because it would rather touch mercury than glass. Water, on the other hand, has a stronger adhesion to glass than it has cohesion to itself. So the water's adhesion to the glass allows it to climb the walls of the glass instead of trying to interact with the water. So it's reaching for more and more glass because the water would rather interact with glass than interact with water. And so what we've labeled these in our chem lab, and which you might have seen in other course, is the direction of the meniscus. Sorry. So the direction of the meniscus here, which hopefully it will let me write. The meniscus, the direction of this meniscus depends on the relative balance of adhesive and cohesive. So if the adhesive forces are smaller than the cohesive, our material pulls away from the glass. If the adhesive forces are greater than the cohesive forces, it will reach up and grab onto the glass and sort of create this indent into the liquid. Or it will be the difference between something being concave or convex meniscus. And so we'll talk about examples of this in more detail. And the way that we can talk about these relative adhesive forces on liquids that maybe aren't sort of climbing the walls is an example that maybe you've experienced personally, which is that if you're wearing a coated raincoat or a raincoat that can sort of repel water, the water might land on the coat, form a bead, and then roll off so that you don't get wet. On the other hand, if you have something like a sweater on, the water lands on your coat and stays on your coat and absorbs through and gets you wet. And so what this process is called is you say that a liquid wets a surface when the adhesion to the surface is stronger than the cohesion forces between the molecules. So with a raincoat, what they've done is they minimize the adhesion of water so that the water stays together and falls off. Minimize adhesion so water leaves. However, on this sweater, the liquid or the water, the rain wets the sweater. It basically falls apart. It would rather interact with the sweater and you get wet. So this is sort of a real world example of the difference between the balances of adhesion or cohesion. So here, the cohesion is smaller. Putting up a fight today. Here, the cohesion is smaller on this right side. And so this sort of absorbing of our liquid into a material can also be used to start to talk about the way that capillary action works. And so capillary action is when a liquid flows within a porous material due to the attraction of the liquid molecules to the surface of that material or to other molecules that have been absorbed. And so in case you don't know this language, so porous materials are materials with lots of space or holes. And so if a material is porous, it's possible for the liquid to fill in those spaces and use those spaces to climb up in the material. And so a lot of paper products and cloth products have long molecules that end in OH groups. And those OH groups can participate in hydrogen bonding with a lot of the liquids that they absorb. So they can easily absorb things like water or wine, as pictured here. And in addition, you can also see this capillary action happening in small tubes of glass for different liquids. And so water, as we talked about before, likes glass and can actually climb up a glass tube as it does this capillary attraction. So it uses this capillary force to climb the tube. On the other hand, mercury will try to push itself out of the tube via capillary action because it would rather interact with mercury than be touching the glass. And so you can actually see level shifting in capillary action that allows us to understand why, or to see in physical form the ways that the cohesion versus adhesion are balancing out in these systems. And in particular, we can describe how the change in heights that we see for these systems relates to properties such as surface tension or the density of our liquids. And so I'm not going to talk about it in too much detail, but we have an equation that describes the height with which a liquid will rise in a capillary tube. And so the change in height that we can see in a capillary is related to the surface tension of the liquid, the contact angle between the liquid and the glass or the material it's trying to climb, how wide our tube is, how dense our liquid is, or how sort of heavy it is as it climbs up, and gravity. And so we can use this expression to talk about why we see different rises in capillaries and how we can use that to relate it to differences in adhesion or cohesion forces. And so we'll work through more examples on the worksheet, but this is some general properties that we like to look at in liquids, and we'll work to relate them to how it's overcoming different types of intermolecular forces.